We need to have a way to indicate three-dimensional vectors in magnetism because the magnetic field is a three-dimensional quantity. So we're going to do that by taking our two-dimensional arrow and trying to make a third dimension out of it. Here's how we're going to do that. First of all, let's recognize that when we talk about an XY coordinate system, generally X means horizontal and Y means vertical. How are we going to make a Z out of that? How are we going to add a Z coordinate to our XY coordinate system so that we have a third dimension? Here's how. First of all, let's recognize that we're representing directions using arrows, vectors. I'm going to draw a large three-dimensional arrow that is pointing parallel to the X direction. There's my large three-dimensional arrow. Now I want you to imagine that I pull that arrow out of the plane of the paper and I set it down with its tail sitting on the paper and I'm looking down on its head. If I do that, here's what I see. When I look down, I see the tip of the arrow, and so I would represent a vector that is coming out of the page, the direction of a vector that is pointing toward me as a point or a tip. Go back to this large three-dimensional arrow that's in the plane of the paper, and imagine pulling that arrow out and sticking the tip into the page. And if I do that and I look down on it, what do I see? Well, what I see is the tail of the arrow, something that looks like this. These X's or crosses are meant to represent the fletching that you would see, the feathers on the end of the arrow. So whenever you see a symbol that looks like that, what that indicates is a vector that is directed into the page. We're going to be interested in representing magnetic field vectors and force vectors and velocity vectors, charge motion vectors using these symbols. So far, we've been doing qualitative sorts of descriptions about magnetism. What we want to do now is to discuss some quantitative things. How can we put numbers to this? And it turns out that there is a way to measure forces and distances and magnetic field strengths. Let's introduce some notation. The variable we're going to use to represent magnetic field is the letter capital B. It is a vector because the magnetic field has a direction. It may be that the direction is a different point, a different direction at different points in space, but at a given point there will be a definite direction of the magnetic field. If I put a compass at a certain point in space, the compass is going to point in a certain direction. And we define the direction of the magnetic field to be the direction that the north pole of a compass will point when it's placed in the magnetic field. That is a very important point. I'll repeat that again. The direction of a magnetic field at a certain position in space is defined to be the direction that the north pole of a compass would point when it's placed at that position in space. If we want to know what the map of a magnetic field looks like, then what we would do is to take a compass and put it at various positions in space, draw a bunch of arrows, and then hook those arrows together, so to speak, in lines of force, and that's going to show us what the shape of the magnetic field looks like. We can measure the strength of the magnetic field using several different kinds of units. The MKS unit for magnetic field strength, or the SI unit if you prefer, is called the Tesla with a capital T. On the AP exam, the Tesla is going to be the most important unit that you're going to see for magnetic field. Another unit that's commonly used is called the Gauss. In North America, the strength of the Earth's magnetic field is about 10 Gauss, not a strong field. It turns out that 1 Tesla is equal to about 10,000 Gauss. Not about, it's exactly 10,000 Gauss. One other unit that you'll see from time to time is something called a Weber per square meter. We're going to see in a later lesson when we deal with Faraday's law of electromagnetic induction that there is a quantity that's called magnetic flux, and the magnetic flux is given in a unit that's called Webers. There's a relationship between the magnetic flux and the area through which that flux passes. That relationship then brings us to a connection between Teslas and Webers. For our purposes, a Tesla is equal to a Weber per square meter. As far as I know, there's not a common unit in English units for magnetic field strength, and so these metric units are the ones that you're always going to see. Now, what about important equations? Ultimately, we want to to be able to work with numbers. We're going to introduce one equation here, and we're going to see that it's going to keep us busy for quite a while. It is called the Lorentz force on a moving charge in a magnetic field. Incidentally, these units, Tesla, Gauss, Weber, and this name Lorentz are all important historical people, physicists who worked on these things. Nikola Tesla was a brilliant Eastern European man who worked for George Westinghouse in Westinghouse's company against General Electric, who was Edison's company, in trying to establish electricity generation in the United States. Carl Friedrich von Gauss is the same Gauss that helped to develop many things in calculus. Heinrich Lorentz did a lot with electromagnetism. I'm not sure I know who Weber was. I'd have to look him up on Wikipedia. That would be the first place that I would go to find him. The Lorentz force. Here is the equation. It's a vector equation. Let's suppose that I have a region of space represented by these four lines here that have a magnetic field that has a magnetic field strength B. In that region of space, let me allow a positive charge to move. This positive charge has a quantity of electric charge Q, and the charge that enters the magnetic field has a velocity v, and that velocity is a vector, so it has a speed and a direction. Now the way that I've sketched this velocity is I've injected the particle perpendicular to the magnetic field lines. It need not be perpendicular to the field lines. It could be any direction that I wanted, but whatever direction that it makes, it will be measured with an angle theta between the velocity vector and the magnetic field lines. In this case, the angle theta is 90 degrees. What force due to the magnetic field and charge motion will the charge experience when it's placed in the field? Here is what that force is mathematically. The strength of the force, B with the force with the subscript B means a magnetic force, B being the magnetic field, is equal to the quantity of charge Q times the velocity V crossed into the magnetic field. F is equal to QV cross B. This is a vector equation, and this cross product is something that we have seen before. It represents a magnitude that is related to the direction between the vectors that are being crossed into each other. V cross B represents a product, a cross product. Here's what it looks like. The magnitude of the Lorentz force is equal to the quantity of charge Q times the magnitude of V, which is the speed of the particle, times the magnitude of the magnetic field strength, times the sine of the angle between the velocity vector and the magnetic field. So if you want to figure out what is the strength of the force, then you can do it using non-vectors, just taking the magnitudes and then multiplying by the sine of the angle between the velocity vector and the magnetic field strength. Now, how do we determine the direction of the vector? It turns out that the direction is given by something that are called right-hand rules and left-hand rules. And these rules are not easy, and there's more than one of them. We're going to introduce the right-hand rule for the force on a charge moving in a magnetic field. For right now, we're going to concentrate on the right-hand rules. Right-hand rules are for positive charges. Left-hand rules are for negative charges. And it turns out here is the reason that physicists have stuck so long to conventional currents being represented by the direction of positive charges. And it has to do with the way that magnetic field directions are associated with charge motion. So let's begin with the right-hand rule for positive charges. The right-hand rule for positive charges moving in a magnetic field says that you allow different parts of the anatomy of your right hand to represent certain vectors, and the directional relationship between them shows you the direction of those vectors. In this rule, you allow the fingers of your right hand to represent the direction of the charge motion. In other words, the fingers of your right hand point in the direction of V. If your hand is extended flat with your thumb perpendicular to your fingers, then the open palm of your hand represents the direction of the magnetic field. When that happens, then the thumb of your right hand represents the direction of the magnetic force on the moving charge. So if you know any two of these directions, you can figure out the third one by orienting your right hand in the appropriate way. This is going to take some practice, and we'll have opportunity for that in the coming days. So now, let's do some numerical problems. Here's the first example. A proton moving with a velocity of 305 meters per second enters a magnetic field that is perpendicular to the plane of the paper as indicated. The strength of the field is 44 teslas. Find the magnitude and the direction of the magnetic force on the proton as it enters the field. We see here that the direction of the velocity is to the right. That's going to represent the fingers of our right hand when we apply the right hand rule. This magnetic field is represented by dots of arrows pointing out of the page, and they tell us what the strength of the magnetic field is, 44 Tesla. Now, I'm going to work on the direction part first, and then we're going to calculate the force. I want you to imagine that the magnetic field is confined to this red rectangular box that I've sketched around these arrows that are pointing out of the page. Let's apply the right hand rule. So I'm working on direction right now. This is a positive charge. I'm going to use my right hand, and I'm going to let my fingers point to the right. I'm going to let my open palm point out of the page towards me. And when I do that, I'm going to see that the thumb of my right hand points in the downward direction. So when this proton enters the magnetic field, the direction of the magnetic force is going to be downward as the proton enters the field. So I've sketched here what those three vectors look like. V is to the right. Those are my fingers of my right hand. Now again, use your right hand. This is a positive charge. My open palm is going to be facing me, and the force is going to be downward. Now we're going to see that what happens is as that force pushes perpendicular to the motion, this is a centripetal force. And so that motion direction is going to change, and if the particle makes its way through the field, it's going to continue to be pushed in a direction perpendicular to its motion, and it will follow a curved path. So the trajectory of this particle is going to be downward as shown here. It's as if the particle is traveling in a clockwise direction around the magnetic field lines as it makes its way through the magnetic field. So to summarize, figuring out the direction of the force, I'm going to use my right hand because this is a positive charge. So I take the fingers of my right hand and I point them in the direction of the velocity. I take my open palm and point it in the direction of the magnetic field. And whichever way my thumb points, in this case downward as the particle enters the field, is going to be the direction of the force. Now, what is the strength of the force? Well, let's apply the Lorentz Force formula. F is equal to QV cross B, where F is equal to Q times V times B times the sine of the angle between V and B. In this case, the magnetic field is always out of the page. The velocity is always in the plane of the page, so the angle between B and V is always 90 degrees, no matter what the trajectory of the particle is. If theta is 90 degrees, then that means that the sine of theta is always equal to 1. So the Lorentz force is going to be Q times V times B. And those are numbers that I know. Since this is a proton, the charge on the proton is 1.6 times 10 to the minus 19 coulombs. So now let me put those numbers in, and let's figure out what the force is. And now I substitute the numbers into my calculator, and I get a result. I get that the magnetic force is equal to 2.15 times 10 to the minus 15 newtons.